Scaling up a bioprocess, taking that amazing result you got in the lab, and turning it into a full-scale production run, it's one of the biggest challenges in biopharma. But what if I told you there's a hidden variable, kind of like a silent assassin, that could completely derail that entire journey? Well, today we're going to shine a bright light on what might be your biggest process blind spot: dissolved CO2. Okay, so our story starts where all great bioprocesses do, right? In the R&D lab. This is the place where everything feels possible, full of optimism, and honestly, results that look incredibly promising on the surface. And this is what we call the lab illusion. You've got your happy flasks, right? The cells are thriving, your yield looks amazing. It's so easy to feel confident when everything seems to be going this perfectly. But here's the thing. That perfect picture is creating a really dangerous false sense of security. So why does everything look so good here? Well, it really just comes down to simple physics. In a little flask, you have a really high surface-to-volume ratio, so any CO2 the cells produce, it just vents right out into the air. No big deal. This creates that classic, what you see is all there is trap, where CO2 isn't even on your radar as a potential problem. And that leads us to the million-dollar question, right? What happens when you take this seemingly perfect lab process and try to make it big? This is exactly where we run into what's called the scale-up trap. See, moving to production isn't just about making everything bigger. No, you're stepping into a completely different environment, one where a hidden danger is just waiting for you. Because the moment you move into a large production vessel, the entire game changes. That lovely high surface-to-volume ratio you had, it's gone. Now it's much, much lower. And all that CO2 your cells are pumping out, it can't escape anymore. It gets trapped, it accumulates, and that dissolved CO2 officially becomes our hidden assassin. What follows is this absolutely devastating chain reaction. First, the trapped CO2 makes your media acidic, so the pH drops. Your automated systems see this and, well, they panic, dumping in base to try and fix it. But constantly adding all this base makes the osmolality spike. Suddenly, your cells are in this totally unstable, stressful environment. And the crucial thing to remember is, stressed cells don't perform. This leads to a total yield crash, where both the amount you get and its quality just plummet. This is the blind spot.
Okay, so we've seen what goes wrong. Now let's really dig into the why. Why is this one parameter so fundamentally important to get right?
Well, it's not just us saying this is important. According to FDA and PATE guidelines, dissolved CO2 is officially defined as a critical process parameter, or a CPP. And that's not just a friendly suggestion. It means that if this parameter varies, it directly impacts the quality of your final product, so you must monitor and control it to get the results you want. Part of what makes CO2 so darn tricky is that it kind of has this double personality. On one hand, it's a waste product from your cells just doing their thing, and you need to get rid of it. But on the other hand, it's a key part of the bicarbonate buffer system that you are actively using to control your pH. So it's both the problem and part of the solution at the same time. And this means you're walking this incredibly fine line. You have too little CO2, and your cell growth just slows way down. But you have too much, and it's literally toxic. It tanks cell viability, and some studies have shown it can cause a shocking 70% decrease in protein titer. I mean, a 70% drop? That's a total disaster for your yield. You've got to stay in that perfect little window. Now, you're probably thinking, okay, it's critical. I get it. But surely we're already measuring this, right? Well, this is where things get really complicated. Let's walk through why the common measurement methods are like a maze that often leads you in the wrong direction. And this really is the central question we have to ask ourselves. Are the tools that most of us are using today actually good enough for the job of managing this critical parameter? Let's start with the classic method, offline analyzers, like a blood gas analyzer. You pull a sample and take it to the lab. The problem is, just the act of taking that sample can introduce errors. Any change in pressure or temperature can throw off the CO2 reading. Plus, the data is so infrequent, we're talking maybe 3 samples a day. You just can't use that for real-time automated control. It's like trying to steer a ship with updates from hours ago. All right, so what about online off-gas analyzers? They're better because they're real-time, but they measure the CO2 in the headspace. That's the gas above the liquid, not in the liquid where your cells are actually living. They work on this assumption that there's a perfect balance between the gas and the liquid, which in a dynamic bioreactor often just isn't true. The biggest danger here is that you can seriously underestimate how much dissolved CO2 is actually stressing out your cells. So the next logical step is an inline sensor, right? Well, the traditional ones are electrochemical, based on something called the Severinghaus principle. We're talking technology from the 1950s. And while they measure in the right place, they are a total maintenance nightmare. You're constantly replacing membranes, replacing electrolyte. They're notorious for drifting after sterilization, and the whole calibration process is just clunky and full of ways to make mistakes. So if we lay it all out, the picture becomes crystal clear, doesn't it? The offline BGA fails on all three counts for process control. Online off-gas? Sure, it's real time, but it's not the right data, so you can't get accurate control. And those old inline sensors? They're getting closer, but they fall down hard on maintenance and reliability. Not a single one of them checks all the boxes you need for truly robust process control. So after all that, all those problems, what's the actual answer? The process is begging for a true, modern, real-time solution. And the solution, when you boil it down, is actually pretty straightforward. It's direct, real-time control of the dissolved CO2. When you can actually see and control what's happening inside the liquid in the moment, you can finally maximize your titer and get predictable, successful scale-up every single time. So how is this even possible with modern technology? Take a look at this. This is an optical sensor, and it is an absolute game changer. This technology solves every single one of the old problems we just talked about. It's based on NDIR, or non-dispersive infrared optical tech. It gives you a direct inline measurement, so you're seeing what matters, exactly where it matters. Because it's a solid-state sensor, there's no drift and no electrolyte to replace. That means it's basically maintenance-free. So you finally get accurate, robust data that you can actually trust for true process control. And this really brings us to the bottom line of this whole explainer. It is time to stop guessing and finally start controlling. You know, the source material puts it perfectly. The ultimate goal is a solution which enables the proper control of CO2 as a critical process parameter at the bioreactor. It's all about making that fundamental shift from reactive damage control to proactive process mastery. So I'll just leave you with this final thought. Your process is scaling up. You've perfected it in the lab, that's awesome. But is your CO2 control strategy actually ready for the real world? Are you finally measuring that hidden assassin, or are you still flying blind, straight into the scale-up trap?